As we have seen, a transistor is the fundamental building block in an RF power amplifier. Let's look into the different kind of transistors that are used in RF applications. The first one is the more familiar BJT, the bipolar junction transistor. As the name suggests, it's bipolar. That means the currents are due to both the majority and minority carriers. There are both a P and N junction over there. Essentially the BJT acts like a current controlled device where you have a certain base current IB and there is a corresponding collector current IC, and usually the IC is going to be beta times IB, with usually beta being the current gain, which is in the order of 100. The characteristic of a BJT is that the input impedance is low. And it has a medium switching time, meaning it takes a certain time for the transistor to switch, and it is typically used for low frequency applications. Low frequency applications may be below 1 gigahertz, so on and so forth. So it is good for what is called as sub gigahertz applications. The second kind is the field effect transistor. Unlike BJT, this is a monopolar device where the current is either due to the P channel, due to the holes, or due to the electrons. There is no both P and N semiconductors there. In essence, this is a voltage controlled device. Unlike the BJT, it's a voltage controlled device, and it has a very high input impedance. Being voltage controlled. So the current through the drain is controlled by the VGS, the voltage VGS, rather than the current that flows through the gate. So it's going to be a high impedance device. What we are looking in here is going to be a high impedance. So it is having fast switching speeds, and so can be used for high frequency applications. And high frequency meaning it can be used for sub 6 gigahertz, beyond 1 gigahertz frequencies. The third category is the high electron mobility transistor, where essentially it is like a FET, but essentially the channel is going to be a very thin layer, and usually it's going to have two different materials for the channel stacked up as in a layer, and because of that it is used for very high frequency applications like microwave frequencies beyond even 6 gigahertz. And by having a very thin layer of the channel, it also has very good low noise performance. Unique about this high electron mobility transistors is the low noise performance. Now, if you take a look at the semiconductor material itself that the channels are made of in transistors, there can be different categories. In essence, the two major classifications is class 4 and a combination of class 3 and 5. We know that all semiconductor materials fall under the class 4, including silicon, germanium, so on and so forth. Now, BJT's metal oxide semiconductors, they're made of silicon, but there can be a combination of silicon and germanium. If you look at the periodic table, the class 4 elements with valency 4, all those materials in that can be used for semiconductors except carbon. So the silicon germanium is good for having higher cutoff frequencies, is used for high frequency applications. Typically silicon is used for CMOS. Silicon carbide, on the other hand, has a very high power density, can have a high power handling capability. But not only just class 4 elements, a combination of class 3 and class 5 elements, meaning like a combination of gallium and arsenide, combination of indium and phosphide, or gallium and nitride can be used as the semiconductor material in the transistor. And unique to these, some of them have advantages. For example, gallium nitride has very high power handling capabilities. The density, the power handling density is pretty high. That means the form factor of the transistor can be very small, yet it can handle very high power. So what you can see here is an illustration of the frequency of operation and the power that the transistor can occupy. Typically, silicon based transistors maybe can be used up to 1 gigahertz, sub 1 gigahertz applications. But if we are going beyond 1 gigahertz, materials like silicon germanium, which has a limited power handling capability, or gallium arsenide, which is very commonly used, which can have a higher power handling capability. But more research trend is to be able to stretch the frequency of operation beyond 10 gigahertz. Like for example, the 5G technology is going to have operations at 28 gigahertz. So these, along with very high power handling capability, we would need to go for gallium nitride or silicon carbide kind of technologies.